This is the first lecture for Chapter 7 for Stats 253, and in this lecture I'll talk about the central limit theorem and the point estimate. This is covered in section 6.9 in the text. Of course, the big question is statistics is, after you've made a sample of a population and come up with some measurement, how close is that result that you got for the sample to the actual value for the entire population? You would like to say it's completely the same, it's right on, but you can't really say that, all right? It doesn't happen. Instead, the question is answered as an estimate, and there's two estimates. One's called a point estimate, in which you're giving one value and saying this is fairly close to the result, to the value that would be for the entire population. The other is to give an interval called a confidence interval and a confidence level associated with it. With this, for example, you would say I am 95% certain that the mean for the general population falls between 2 and 4. That's an interval estimate. The first thing to note is the central limit theorem. What does the central limit theorem, what is the subject of the central limit theorem? Okay, if you are sampling something that, say, comes off a production line, you might pull so many samples off every couple hours. The collection of all those samples is what the central limit theorem is going to address. The averages from the collection of the samples. Now, remember, in casual speech, when we say a sample, we usually think of one. Like you order a sample of fabric, they're going to send you one little square of it. But here, the sample would mean it would have a certain size, and the sample would be the number that you pulled off the production line, for example. So you pull these samples of a certain size off the production line, you average them. Now you take all those averages, and that is what we're going to talk about. This is an example of what I was trying to say. So you are a CD manufacturer, and every hour you pull 25 CDs off the line and you check them. You're going to measure the radius. All right. So of these 25 CDs, you pull them off, you measure the radius, and then you average them. That is one data point for the central limit theorem. So you do that over and over again. For example, if you did that for the month of January, you would have 744 averages from 744 samples, and each sample would have 25 CDs in it. Now, according to the central limit theorem, the histogram of those averages will be approximately bell-shaped. And that is supposedly true no matter how the population is organized, whether it is normally distributed or not. The more samples you take off the assembly line, the more averages you graph, the more that this histogram is going to look bell-shaped. If you just do a few, obviously you can't really tell much, but if you keep sampling over January, February, March, April, May, and then you graph all of those, which would be like 4 times 744, something like, what about 3,500 values? That's going to look very bell-shaped. In the center of that is what's called the distribution mean. So it is the mean of the means. Okay, it's the average of the averages. The central limit theorem states that the distribution mean is equal to the mean for the entire population, and that's why they give it the symbol mu. This graph, which I borrowed from somewhere on the internet, illustrates the idea of increasing the number of samples that you're graphing. In this case, 100 was graphed, and you can see it sort of looks bell-shaped. But now I like this because it claimed that the number of samples was infinite. So with an infinite number of samples, you can see that this histogram is very bell-shaped. So these are histograms based on the averages. Okay, the averages from each sample that you pulled off, or whatever you're sampling. Okay, for example, if this was the sorry, all this extra stuff on. So now what happens if you increase the size of the sample? For example, instead of taking 25 CDs, you take 50 every hour or 100 every hour. As you accumulate all these averages, the curve will still look bell-shaped, the mean will still be in the same place, but the curve itself will become more narrow as the sample size increases. This is for 100, n of 100, and here's n of 25. So these are the two parameters. The more samples you're looking at, the more that histogram looks bell-shaped. The larger the sample size, the narrower the bell-shaped curve, or the approximated bell-shaped curve. You can sort of think of it just in terms of numbers. If my sample, that's in quotes, consisted of the entire population, and I took its average, that would be the same as the average of the population. In that case, the bell-shaped curve would be just a line. So you can think of it in that terms. As you take more and more samples, you're actually just taking more and more of the population, and of course the result would be closer to the population, assuming you're picking your samples correctly.